Okay, so now we're doing question 8F of your homework. So it asks you to write an equilibrium constant for the following reaction as a mathematical expression comprised of the concentrations of reactants or products. All right. I forgot to include the reaction on this. All right, these problem sets are all new, so they're going to have some typos. Sorry about that. All right. The reaction be ATP decomposing into ADP and phosphate. All right, hopefully you can figure this out by looking at some of the questions that follow. If not, I'm not going to grade this particular problem because of some things that were missing in it. But all right, this is the reaction here. So if I was to write out an equilibrium constant expression comprised of the concentrations of reactants and products, so the equilibrium constant for this, then it's going to be concentration of products times each other over the concentration of reactants. So this is our equilibrium constant here. Make this a little prettier here. There we go. All right, that's the equilibrium constant. All right, so that part's pretty easy. So subpart 1 here is actually the hardest out of all of these. So let's go ahead and get to it. So all right, it says if half millimolar ATP was placed into solution and the reaction was allowed to come to equilibrium, what would the final ratio of ATP to ADP be if the delta G for the reaction is negative 30.5 kilojoules per mole? All right, so if you're faced with a question like this, all right, one of the first questions, it's clear that we're going to have to do a calculation because I'm asking about numbers. I'm giving you numbers. All right, the question is which equations am I going to need to use? Well, here I'm giving you information about the delta G of the reaction, so the free energy. So we know we have that. We also have concentration information here. So we're given concentration information about ATP, and we're being asked also for concentration information in the end here. So we're looking for an equation that has delta G in it and concentration information. And it's also important to be aware of what's not in here or not discussed. So I'm not discussing actual delta G's or anything like that. All right, so the equation that you should use for this one is the delta G naught equals negative RT times the natural log of KEQ. All right, so in this particular question, I didn't say that this was the delta G naught, negative 30.5, but you don't always have to. Sometimes that's just kind of implied by the phrasing of the question. In this particular case, it was. Also, you might be wondering, well, Dr. Brandon, she didn't give us temperature. All right, well, that's true as well. So this is a general rule for you guys. If I neglect to give you temperature, assume standard conditions, 298 Kelvin for the T. All right, so all right, so let's start plugging in what we have here. So we have our delta G, negative 30.5 kilojoules per mole equals negative. Now we want to use the right number for R. So on the left I have units of kilojoules, so I'm going to use an R gas constant that also has units of kilojoules. So 0.0083 kilojoules per mole Kelvin times 298 Kelvin times the natural log of KEQ. We're going to just leave this part, the KEQ, alone for a little bit here. All right, so what I'm going to try to do now is get the KEQ alone on one side, and you'll see why. Because the other information I'm given an initial concentration of a reactant, and I'm asked for concentration information about the reactants and products. Well, those concentrations are contained in the KEQ here, so I'm going to try to isolate that. So what I'm going to do is I'm going to divide both sides by the negative 0.0083 times 298. Oops, too many zeros. All right, and then to get rid of the natural log, I'm going to take the e to the both sides. All right, and that basically undoes the natural log. So we'll have e to this power and e to that power on both sides here. So let's do some math. So 30.5 divided by 0.0083 and divided by 298. And then we're going to take e to that power. All right, and so we end up with the equilibrium constant equaling 227,000. I'm just going to round. It's a very large KEQ. All right, just as a quick check, is this what we'd expect? Well, a negative, very negative delta G, negative 30.5. So this reaction will be spontaneous and head towards the right. So having a large KEQ is consistent with that, because this would imply that we have more products than we do of reactants. So again, saying the equilibrium lies to the right. All right, so we know that the KEQ is equal to this relatively large number now. All right, so now let's start looking at, we're going to kind of combine the very first thing we did in the first part of this multi-part problem here with this. So we're going to add in the concentration information in here. So our ADP and phosphate concentrations go on top, and our ATP concentration goes on the bottom, and this is equal then to 227,000. All right. Now, I give you guys information about how much ATP we started out with, right? Implying that some of that ATP is going to get converted to ADP and phosphate until it comes to equilibrium. So hopefully this type of a problem rings some bells from Gen Chem and everyone's favorite thing, the ICE tables, right, where we have I stands for the initial concentration, C is the change, and E is the equilibrium values. So we're going to make this table here and have ATP, ADP, and phosphate. Oops. All right, well, in our initial concentration of ATP is 0.5 millimolar. Now, when we're working with equilibrium constants, I can't stress this enough because this will come up again in number 2 here, which I'll make as a separate video. But the concentrations have to be in units of molar. All right, so the 0.5 millimolar ATP is actually 0.0005 molar. All right, and then also implied in here is that we're not starting off with any ADP or phosphate, because I didn't mention that we had any. All right, well, in order for this system to come to equilibrium, we have to lose some ATP, and for every ATP we lose, we're going to gain 1 ADP and 1 phosphate, all right, because of the stoichiometry of the reaction. But we don't know how much. That's what we're after, all right, at least in part. All right, so we're going to lose X amount of ATP and gain X amount of ADP and phosphate. So our equilibrium concentrations then are going to be 0.0005 minus X for ATP, and then just X for ADP and phosphate. Okay. So I'm going to erase some of this here, give us a little bit more room to work. All right, there we go. All right, so let's plug in these equilibrium concentrations into our expression. What we end up with now is we have X times X over 0.0005 minus X. Now, I've told some of you guys came by my office, and I actually realized after the fact that I told you some stuff incorrectly here. All right, in some cases, when you're doing subtractions with variables like this, it can be okay to drop the x term. But the only time you can do this is when that x value is negligible. All right, well, in our particular case, because if you think about it, our equilibrium lies very far to the right, correct? So the amount of ATP that we're going to be losing, this negative x, is not going to be a negligible amount. So we actually do have to leave it in this equation. All right, so we end up with this expression. All right, now we have to solve for x. All right, so the way we're going to do this is we're going to try to get everything on one side of the equation. So it's kind of an intermediate thing. We'll cross multiply both sides by the 0.005 minus x. And so we're going to end up with end up with 113.5 minus 227,000x. Double check that. Yep. All right, now we want to get everything, all our terms on one side of this equation. Sorry, there's x. I left that off. All right, so we're going to subtract 113 both sides and add 227,000x to both sides. All right, so we're going to end up now with x squared plus 227,000x minus 113.5 equals 0. All right, now at this point we're ready to use the quadratic equation. So this is a relatively long problem. It's extremely unlikely I will ask you a problem this difficult on an exam. All right, on problem sets, I will often ask you things that are harder than exam questions because, hey, you have more time. This is your chance to practice some of these skills. So, all right, the quadratic equation is that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, now our b, so we have, start plugging stuff in there. So we have negative 227,000 plus or minus, we have to consider both, our b squared, so this is going to be a big old number, 227,000 squared, minus 4 times a, which is 1, times c, which is negative 113.5. All right. All of that now over 2a, which in this case is just 2 times 1, or 2. All right. So let's start simplifying this down a little bit. So 227,000 squared minus 4 times negative 113.5. And then we'll take the square root of that. All right. So we end up with negative 227,000 plus or minus a number that is very, very close to that, 227,000 .001. All right, all over 2. All right, so now the addition case here is the one that's going to give us the actual correct amount. Right, you can calculate both of them and test them both, but the adding one is the one that's going to give us the correct amount. So all right, we're going to get here that x is equal to 5 times 10 to the minus 4. All right, now when we go to put this back in here, because of the rounding I did earlier on in coming to the 227,000. All right, if we put 5 times 10 to the minus 4 in here for x, all right, we're basically going to end up with our equilibrium concentrations of ATP being 0 and ADP and phosphate being 5 times 10 to the minus 4. All right. Way to correct for this is not to round like I did in the middle of the problem. But if you happen to do this, this would be okay. So now we know the final concentrations of ATP, ADP, and phosphate at equilibrium. All right, what is the question actually asking for? It's asking for the ratio of ATP to ADP. So in this case, it'd be 5 times 10 to the negative 4 molar to 0, or kind of an infinite ratio. So because of the large equilibrium, it is actually really important that I didn't round back here. But like I said, I would be okay with you guys leaving it at this point. But you should end up, regardless, with a very, very large ratio, perhaps not infinity. All right, so I'm going to stop this video and then make number 2 in another video.